Last talk of this afternoon session will be given by Wenrui Ye from the University of International Business and Economics, Beijing. His talk is on Bochner-Riesz means for the Dunkl transform.
Okay, thank you. First of all, I want to thank all of the organizers to organize this conference and give me a chance to give a talk at here. And today, the topic of my talk is Bochner-Riesz means for the Dunkl transforms. And this is the outline of my talk. I will first introduce some basic setting in the Dunkl theory, include the weight functions and the Dunkl transforms. Then I will talk about some of our results about the Bochner-Riesz means, the restriction theorem, the Littlewood Paley inequalities for the Dunkl theory. And this work is a joint work with Dr. Feng Dai. Let me first introduce the weight function we used in the Dunkl theory. We see a set R is a root system if this set is a finite set of non-zero vectors, and if for any two vectors u and v in this set R, then the reflection of u about vector v is also in this set. And since the reflection of u about v is actually equal to the reflection of u about minus v. So sometimes we just need the positive root system. We can fix the vector v0, and the positive root system is the set of vectors whose interproduct with v0 is non-negative. And the group that generated by the reflections of the root system is called the reflection group. And we can use the reflection group to define the multiplicity function. And these functions are from the positive root system to the non-negative real numbers. And it is satisfied this property here, kappa u equal to kappa v, if v is the reflection of u about some vectors w in the root system. The weight function that we used in Dunkl theory is this weight. It is a product weight. And since this power is the multiplicity function, so clearly this weight function is invariant under the reflection group G. And if we choose C2D as our reflection group, and if we use the standard Euclidean base as the positive root system, and in this case our weight function can be simplified in this form. The harmonic theory with the Dunkl weight is called the Dunkl theory. And for this theory, on one hand, when we add this weight function, then the measure is no longer translation invariant, and it is not rotation invariant. So on one hand, we weaken the translation invariancy and the rotation invariancy. But on the other hand, almost every result in the classical Fourier analysis continues to the Dunkl theory. So in this sense, the Dunkl theory looks very beautiful. And the LP space are the space of functions whose weighted LP norm is finite. There are two important operators in the Dunkl theory. One is the Dunkl operator, and the other one is the Dunkl intertwining operator. The Dunkl operator is defined by this equation, and at here the first term is the partial derivative of this function with respect to the j's coordinate, and the second term is the difference of this function. And this Dunkl operator plays the role of partial derivatives in the Dunkl theory. Then let me introduce the intertwining operator. Let p and d be the set of d-variable homogeneous polynomial of degree n, and let pi d be the space of algebraic polynomial on the Rd. And the Dunkl intertwining operator is a linear operator from pi d to pi d that determinant uniquely by the following three properties. The composite of v kappa with dj equal to the partial derivatives composed with v kappa, and v kappa 1 equal to 1, and v kappa of a d-variable homogeneous polynomial is another homogeneous polynomial of degree n. And after we got this intertwining operator, we can use it to define the Dunkl transform. The Dunkl transform is defined by this equation. And here, this E kappa is defined by the Dunkl intertwining operator. And for the unweighted case, if our weight function equal to 1, in that case, this E kappa is just equal to an exponential function. And in this case, the Dunkl theory become the classical Fourier. The Dunkl transform is the classical Fourier transform in the unweighted unweighted case. So and this is the case when f is a weighted L1 function, and if f is a LP function with p greater than 2, we can define the Dunkl transform of this function in distributional sense. Many properties of Fourier transform carry out to the Dunkl transform. For example, if our function is a weighted L1 function, then the Dunkl transform of this function is continuous function, and it is vanished as the norm of c goes to infinity. Secondly, the Dunkl transform of d kappa alpha f equal to minus I x power alpha times the Dunkl transform of f. And from here, you can also see the Dunkl operator plays the role of partial derivatives in the Dunkl theory. But the most two important properties of Dunkl transform are the Poincaré theorem of L2 function and the inverse formula for the weighted L1 function. Here, if both f and the Dunkl transform of f are in L1, we can use the Dunkl transform of f to recover f at almost everywhere. But the condition that the Dunkl transform of f is integrable, this condition is actually a very strong condition. And sometimes it is not easy to check. So to recover a L1 function by its Dunkl transform, we can consider the Bochner-Riesz means. The Bochner-Riesz means for the Dunkl transform of L1 function is defined by this equation. And here, if this index delta is very large, then the convergence of the Bochner-Riesz means can be very well. So our first week is to study the minimum index such that the almost everywhere convergence of Bochner-Riesz means holds for weighted L1 function. Let's first see some related result. The first result is given by Sankwalou and Xu Yuan in 2005. They proved the Bochner-Riesz means converges to f in L1 norm if and only if this index delta is greater than lambda kappa. And here lambda kappa equal to d minus 1 over 2 plus kappa norm. And the kappa norm is the sum of all coordinates of kappa. And for the unweighted case, this is a classical result given by Stein. He proved that the Bochner-Riesz means of integrable function f converges to itself at almost everywhere if and only if delta is strictly greater than d minus 1 over 2. And this is also the index when our kappa equal to 0. Usually in the Dunkl theory, this index lambda kappa plays the role of d minus 1 over 2. We usually use this lambda kappa to instead of d minus 1 over 2 in the Dunkl theory. So we proved for the weighted case, if kappa is not 0, the Bochner-Riesz means of weighted L1 function converges to itself at almost everywhere for all L1 function if this delta is greater than or equal to lambda kappa. This result is actually a little surprising because in the unweighted case, this almost everywhere convergence does not hold on the critical index. That means if delta equal to lambda 0, this convergence does not hold. But we proved in the weighted case, when delta equal to lambda kappa, this convergence is also true. The way we prove this this convergence is to use the maximum Bochner-Riesz operator. And we proved if kappa minimum, here the kappa minimum is the minimum value of all coordinates in kappa. If kappa minimum is greater than 0, and if delta is greater than or equal to lambda kappa, the maximum Bochner-Riesz operator has the weak type 1-1 inequality. And when under the case if kappa minimum equal to 0, and if kappa norm is greater than 0, this means at least one of the coordinates in kappa should be positive. In this case, and when delta equal to the critical index, we got another weak type estimate of the maximum Bochner-Riesz operator. The only difference is on the right-hand side, we add one more log term. But both of these two weak type estimates implies the almost everywhere convergency by applying a density argument. After we got the weak type 1-1 inequality, we can use it to prove the strong PP inequality by using the interpolation theorem. But this result is not very good, especially when P is greater than 2. What is the best result for the strong PP inequality of maximum Bochner-Riesz operator for the classical Fourier transform? It is a result given by Michael Kreis in 1984. He proved if P, delta, and D under these three conditions, then for all LP function is maximum Bochner-Riesz operator satisfied the strong PP estimate. And we can rearrange this three inequality into this form. These three conditions is actually equivalent to P is greater than or equal to 2 plus 4 over D minus 1, and the delta is greater than this index. And in Dunkl theory, we always use lambda kappa to instead of D minus 1 over 2. So we guess the analog of this result should be a strong type PP inequality under the condition when P is greater than or equal to 2 plus 2 over lambda kappa, and the delta should be greater than the maximum value of 0 and this delta kappa P. And at here, we just use this 2 lambda kappa plus 1 to instead of this D. And we proved this result. If P is greater than or equal to 2 plus 2 over lambda kappa, and if delta is greater than the maximum value of 0 and the delta kappa P, then for all weighted LP function, the maximum Bochner-Riesz operator satisfied this strong PP inequality. And under the condition when P is greater than or equal to 2 plus 2 over lambda kappa, this condition on delta cannot be weakened. That means this inequality is no longer true for the case when this delta is less than or equal to delta kappa P. This is because a result of Dr. Feng Dai and Dr. Wang Heping given in 2010, they proved that if P is greater than or equal to 2 plus 2 over lambda kappa, then the Bochner-Riesz operator, the operator norm is bounded for all LP function if and only if the delta is greater than the maximum value of 0 and the delta kappa P. And since the strong type PP inequality is stronger than the boundedness of our operator norm, so when delta is less than or equal to delta kappa P, this strong type inequality cannot be held. Next, let me introduce a little bit about this condition. This P is greater than or equal to 2 plus 2 over lambda kappa. Why we need this condition? This is because long-standing famous conjecture named the Bochner-Riesz conjecture. This conjecture is stated as followed. When P is greater than or equal to 2, less than 2 plus 2 over lambda 0, this is the D minus 1 over 2. In this case, the operator norm of Bochner-Riesz means is bounded for all LP function if and only if delta is greater than the maximum value of delta and delta 0 p. That means if we can weaken this condition a little bit, that means we solved a part of Bochner-Riesz conjecture, and it is too difficult for me. There are some results on the Bochner-Riesz conjecture. The first result is given by Hertz in 1954. He proved that for p is greater than or equal to 2 and d is greater than or equal to 2, this condition, delta greater than the maximum value of 0 and delta 0 p, is a necessary condition for the Bochner-Riesz conjecture. And Carlson and Sloan proved that for p is greater than or equal to 2 and if d is equal to 2, the Bochner-Riesz conjecture is true. But for the higher dimensional case, this conjecture is still open. Then let me talk about our proof. To prove the strong type PP inequality of the maximum Bochner-Riesz operator, we need two tools. One is the restriction theorem, one is the Littlewood Paley inequality. To prove the restriction theorem, we need to first define the translations in Dunkl theory. And the translation of a Schwarz class function is defined by this integral. And this translation also satisfies some properties that is very similar to the classical Fourier transform. Our first work is to prove this translation operator is a bounded operator on LP. If p is greater than or equal to 1 and less than or equal to infinity. At here, the case when p is greater than or equal to 1, less than infinity, this case is not proved by me. What we did here is just to prove this result when p is equal to infinity, since the L infinity, the Schwarz class is not dense in L infinity. After we got the definition of translations, we can define the convolution. And then let's begin to prove the restriction theorem. Let d sigma be the spherical Vega measure, and let Rf be the restriction of the Dunkl transform of F on the unit sphere, and R star is the dual operator of R. So the composite of R and R star is equal to the convolution of F and the Dunkl transform of the spherical measure, which is defined by this equation. And we proved that if p is greater than or equal to 1, and if p is less than or equal to this index, then the R star f, the p prime norm of R star f is less than or equal to c times the p norm of f. And since the square of the operator norm of R equal to the square of the operator norm of R star equal to the operator norm of R composed with R star, so this R is a bounded operator from LP to L2 if p is greater than or equal to 1 or less than or equal to p kappa. This p kappa is this index. The p kappa equal to this index. And this theorem, we call it the global restriction theorem. It is very similar to the result, one of the results in the classical Fourier analysis. But actually, this theorem is not enough for us, because at here, when we add this weight function will be very, very small near the coordinates plane. So when x is near, when our variable is near the coordinates plane, this global restriction theorem is not enough. So we developed a local restriction theorem. At here, let B be a ball that's centered at omega and with radius theta greater than or equal to a positive number C0. And if f is a LP function supported in this ball, then we proved this inequality. And this, the only difference between this inequality and the inequality in the global restriction theorem is, this is the global restriction theorem, and this is the local restriction theorem. The only difference is on the right-hand side, we add one more term. We add this term. And actually, this term can be, also can be evaluated. This term is similar to this one. And at here, you can see, since when p is greater than or equal to 1, less than or equal to p kappa, 2 over p minus 1 is a positive number. So since this power is a positive power, when theta is very small, if theta is very small, then this term is also very small. So in this case, our local restriction theorem is much better than the global restriction theorem. This is one of the tools that we need to prove the strong type PP inequality for the maximum Bochner-Riesz operator. And the other tools that we need is the Littlewood Paley inequality. And to develop the Littlewood Paley inequality, we first define the AP weight. We see a non-negative local integrable function is AP weight for p is greater than 1, less than infinity, if this weight function satisfies this inequality. And we say it is A1 weight if it is satisfied this inequality. And it is just like the AP weight in the classical Fourier analysis. A weight is AP weight implies it is AQ weight if P is less than Q. And we use this ratio Schwarz function to define our square function. And we proved that if our weight function is the AP weight for P is greater than 1, less than infinity, and if this weight function is invariant under the reflection group Z2D, in this case, the P norm of square function is less than or equal to constant times the P norm of F. And if in addition, we have this condition, then the LP norm of square function is similar to the LP norm of F. And by these two theorem, local restriction theorem and Littlewood Paley inequality, we proved this strong type PP inequality for the maximum Bochner-Riesz operator. Our last result is on the almost everywhere convergence of Bochner-Riesz means. And here we have already got the strong type PP inequality, and it directly implies the almost everywhere convergence at the same condition, under the same condition. That means if P is greater than or equal to 2 plus this term, and if delta is greater than this index, then the convergence of Bochner-Riesz means for LP function holds directly. But although we cannot drop this term when we prove the strong type inequality, we want to drop this term, this 2 over lambda kappa, when we prove the almost everywhere convergence. And we proved that if P is greater than or equal to 2 without 2 over lambda kappa, and if delta is greater than the maximum value of 0 and the delta kappa P, then for all LP function, the almost everywhere convergence of Bochner-Riesz means holds. And this result is the analog of the result of Carbery. And the Carbery's result in the classical Fourier analysis. If we rearrange the conditions of the theorem of Carbery, then it is equivalent to P is greater than or equal to 2, and the delta is greater than the maximum value of 0 and delta 0 P. That means this is the case when our weight function equal to 1. Now we have 2 open questions. The first one is here, if delta is less than this index, if delta is less than this index, we think the almost everywhere convergency does not hold. But at this time, we cannot construct a very good counterexample for this problem. And another question is, since we proved the almost everywhere convergency of Bochner-Riesz means holds for L1 function when delta equal to the critical index. So we also believe that in the unweighted, in the weighted case, this almost everywhere convergency also holds when delta equal to this critical index. But we still do not have a good way to prove this fact. That's all. Thank you.
Well, thank you for your talk. And are there any questions or remarks or comments?
Okay.
So you have some results with AP weights. Is it possible to prove the boundedness of the Bochner-Riesz operator in LP with AP weights also?
Yeah. We defined AP weight, but actually the AP weight is also depend on the Dunkl weight function.
Yes.
Okay.
But for the operator, the Bochner-Riesz operator, you can get the boundedness also with AP weights? You didn't consider that?
Yeah, it's a very good idea. Okay. Thank you. We didn't think about it, this question.
Where did you publish your results?
Sorry?
Where did you publish your?
Oh, for the strong type PP inequality and the local restriction theorem and this Littlewood Paley inequality, we published it on the on transaction of the American Mathematical Society. And our last result, this result, the almost everywhere convergency, I just submitted this result, and I'm now waiting for the result now.
About boundedness of translation operator.
Translation operator.
Yes.
It is also in the paper on the transaction.
So further questions? Seems not to be the case, so then let's thank the speaker again and all other speakers.